Hi everyone, welcome back to another lecture of Phys 4250 or 8250, Design and Application of Lasers. I'm your instructor, Dr. TJ Hammond. We're continuing for Wednesday, October 21st on pulsed lasers. So if you remember last lecture, we talked about Q switching. This is a way of making these giant pulses. So these can be, hundreds of millijoules or, several joule pulses. They tend to have about 5 to 10 nanosecond pulse duration. Oh, I think I meant to change this. 5 to 10 nanosecond pulse duration. They can be a little longer, but they tend to be on the nanosecond, which is about as fast as electronics. But yeah, they can create these massive pulses. And then if you focus them tightly, you can have really, really high intensities. And so as we compare some numbers, Dr. Razy's lab has, an intensity, if you focus it tightly, can get up to 10 to the 18 watts per meter squared. Whereas the sun, even if you focus it extremely tightly, is going to be something like a millionth that. So that's the reason for why we like these the Q-switch pulses. They're really, really big. Today, we're going to talk more about dispersion. I know that this was confusing to some of you guys when I brought this up earlier when we did absorption and dispersion. So I'm going to reiterate that we have an a wavelength-dependent index of refraction, and that's given by this term here. And we kind of derived it earlier. You do a more formal derivation of this in E&M waves, electromagnetic waves. So if you took electromagnetic waves with me, you can review your notes on how we got this this number for the index of refraction, or if you will be taking it with me this winter, we'll show you where we get this number from. But suffice it to say, if you look at the complex response of the electron to the oscillating field, to the electromagnetic field, you saw that there was a real part and an imaginary part, and this is the real part. And so that's the part that we're going to be looking at, is the real part of that complex response, and that is the index of refraction. So the index of refraction squared is given by 1 plus, and then this is kind of more accurate for gases. It kind of works for solids as well and liquids, but it's kind of like a more it's not exactly a quantitative, I suppose, but it gives you some inclination of where this comes from. So number of atoms or electrons that are absorbing or that you're hitting. The electron charge squared over 2 times the mass of the electron times the permittivity of free space. And then we have this Fj, that's just going to be some harmonic oscillator strength. So this depends on what transition we're exciting. Some transitions are more likely than others, and that's just because of the wavelength dependent strength of the oscillators. We have omega j minus omega up here and down here. Omega j is the place for this resonance. So if we were looking at absorption, this would be peaking at this frequency here, or we have a higher frequency here. We have also a resonance here. So that'd be that omega j term. And then we also have the damping factor, this gamma j. And that gamma j gives us how sharp this goes from going up to going down. If you remember from the absorption, it's also how sharp that absorption is. The phase velocity is the speed of light in vacuum divided by the index of refraction. So this is the velocity that you normally think of when you when you think of the speed of light in some material. Is the phase velocity, or the velocity of a certain frequency. But it turns out that phase velocity isn't the only velocity. You also have to think about group velocity. And so once we have pulsed lasers, you actually have to think about how fast this pulse is traveling, not just how fast each individual frequency is traveling. So from Maxwell's equations, we have that each frequency component is going to be a solution to this wave equation, to this second order partial differential equation. where the phase velocity is given by the phase velocity squared, or 1 over it is n squared over c squared. And that's where that phase velocity comes from, is because that phase velocity is the solution to the wave equation, right? So we'll go through this in more detail in class. But basically, you have a wave of a single frequency component that will be traveling with that velocity, the c over the speed of light, or c over the index of refraction, and that will be the speed of light in that medium, the phase velocity. But the thing is, and I guess this isn't playing, is if we have a pulse, then we can have a difference between a phase velocity and a group velocity, where the group velocity is how fast the pulse is traveling versus the phase velocity, which is how fast the wave is traveling. So this is an animation that I stole from Wikipedia, but it's a pretty good animation where the green dots show where there's a minimum of these envelopes, and so that would be the group velocity, and then you have this orange square, and that's following where you have the peak or the trough of one of the waves. So you see that it's a peak there, and now it becomes a trough here. And that's because the phase and group velocities are different, and in fact, I think they're different by a factor of 2 here. That's kind of like an animation that shows you that there can be a difference between phase and group velocities. So it turns out that the group velocity, the phase velocity is that you get the inverse of the phase velocity is k over omega, and it turns out that you can also take the derivative of k and with respect to omega, and that also has units of 1 over meters per second, which is also 1 over a velocity, and it turns out that that is the group velocity, okay? So your assignment is to prove that it's the group velocity. So I won't prove that here in class, but we'll be using this fact throughout this week. So now we have a laser pulse. So not only do we have an amplitude of the electric field, we have the phase velocity here of some frequency component, but then we also have an envelope here, and this envelope, or the pulse, travels with this group velocity, whereas each frequency component travels with this phase velocity here. So an example would be a Gaussian pulse. This is probably going to be the most common envelope that we'll encounter in this course, and probably as you would encounter for most pulse shapes would be Gaussian, just because it has nice Fourier transform properties. But you have this envelope here that's given by this Gaussian envelope, and so now you have this pulse travels with this group velocity here, so you have this time is going to be this retarded time of the time that you actually have minus z over vg, where vg is the group velocity, where the group velocity is given by c over ng, ng being the group index of refraction. Okay, so the group velocity will also be dependent on frequency, right? So the phase velocity is obviously dependent on frequency because 1 over the phase velocity is k over omega. So obviously this is going to be dependent on frequency when you have some material with an index of refraction, because that index of refraction will always be frequency dependent. But the same thing will be true for the derivative of that. So that means that also the group velocity will be frequency dependent. And that's called group velocity dispersion, how we characterize that frequency dependence of the group velocity. And that's because it's how frequency dependent the group velocity is, where the group velocity is already the derivative of k with respect to frequency. So if we take this wave vector k, which is, remember, 2 pi over lambda, and so we have this wave vector k. We want to expand it in terms of a power series. What we get is the first term is just this k of the carrier frequency, which is going to be omega of the carrier frequency divided by the speed of light times the index of refraction at this carrier frequency, whatever this, the central oscillation frequency is. And then because we're taking a Taylor series, we then get the first term is going to be the derivative of k with respect to omega, but that is of course 1 over group velocity, and then that has a multiplied by a linear dependence of omega minus omega c, and so that gives us the first term, and then we have a second term here, which is going to be proportional to the derivative of the second derivative of k with respect to omega squared, but of course di k by di omega is 1 over the group velocity, and so then what we're actually doing is taking the derivative of the group velocity with respect to omega, and so that's why it's called the group velocity dispersion, because it's how much that group velocity is dispersing, how much it's dependent on the frequency. Okay. So you can think of index of refraction throughout the visible would be something like this. So 300 nanometers to your eye can see, from about 350 to 750 nanometers or so. So this is throughout the visible. This is what the index of refraction of glass is. And so there's always a frequency dependence of the index of refraction. So even for, a very dilute gas, something like helium, there will always be a slight frequency dependence to the index of refraction. That's because there's always going to be some portion of the electromagnetic spectrum that this atom or molecule or solid or liquid or whatever it is will always have some region where it absorbs. And if it ever absorbs in some region, then you always have dispersion somewhere, because you always have that omega j minus omega term in the index of refraction. So it turns out that for glass, there's an absorption that's in the UV, at about 100 nanometers, 150 nanometers, and then there's also an absorption at about I think 2,500 nanometers or so. So the visible happens to be between these two absorption regions, and so that's why we get this this wavelength-dependent index of refraction. So think of how a prism works. So you have white light coming in here, red light bends less, and then bends less coming out, and then you have blue light has a higher index of refraction, so that means it bends more from Snell's law, and then on the way out it bends even more, and that's how a prism works, or that's how a grating works, or that's how a rainbow works. And for those of you who like prog rock, there's this iconic Pink Floyd album cover of a prism. So if you can't remember what a prism looks like, you can always think of Pink Floyd. So a gain medium will always have a frequency-dependent index of refraction. It doesn't matter if it's a gas, liquid, or solid. All gain media have to be something. You can't have a vacuum being gain media. So you have to have some kind of gas, liquid, or solid, and because you have some material, they'll always have some region where it absorbs, and if there's some reason where it absorbs, then they'll have an intensity-dependent index of refraction, and so you'll always have dispersion. Okay, so this is how a pulse separates spatially, but why am I talking about this so much when we're talking about pulses? And it's because it turns out what we care about is how a pulse acts temporally. So that's when we talk about this group velocity dispersion. So what happens to a pulse inside of a laser cavity? So if you have a short pulse initially in this laser cavity, say you somehow manage to magically create a 10 femtosecond laser pulse, 10 femtosecond laser pulse with a 1 micron central frequency would look something like this. So this pulse would then hit this gain medium. So say it's a crystal that's 1 millimeter long. If it's glass, of course it wouldn't be glass. Glass doesn't act as a gain medium. But if it were something that were similar to glass, then this 10 femtosecond pulse would stretch out a little bit. You'd see a little bit of stretching, not very much, but just a little bit. And then it would hit this mirror and then bounce back and then go through this 1 millimeter of glass again. And then you see actually it stretches out a little bit more, and then it bounces off of this mirror and goes to this glass again. And after 3 passes, you can see that this was an initial 10 femtosecond pulse, and now it's stretched out to something like 20 femtoseconds. And if it bounced back, went through the glass, and then bounced back and went through the glass again, then after 5 passes, you can see this pulse has decreased in amplitude, and you can see that it's actually stretched out a fair amount here in space. So if there were a group velocity dispersion within a cavity, then the pulse is stretched out more and more with each pass. So if this thing stretched out, or this pulse, rattled around for, say, hundreds of times or thousands of times, then this pulse would just decrease and decrease in amplitude and become longer and longer and longer in time until it's no longer really a pulse. And so this is because we have some net intracavity group velocity dispersion. So in order for us to maintain this pulse, we can have this pulse go through this glass and stretch out, but then we have to have something here that compresses the pulse, that has anomalous dispersion, or has dispersion that's of the opposite sign, so that we get this pulse back to this original shape, and then it can go back through this glass, and then we need something again to recompress that pulse so that it looks like this original shape again, so that after each full pass through the cavity, it comes back to this original shape. If you've ever heard of the term a soliton, this is what that means. So I remember back in the mid-90s, there was a lot of talk about solitons. And so I'm not sure if they're really kind of like a buzzword anymore. But I remember having my undergraduate project where it was studying solitons because they were found to be interesting in general relativity, and people found them in lasers, but they were also, people were finding them in really strange places, like in general relativity and in how black holes were propagating and things like that. But this is what's required of a soliton, is that you need to have net group velocity dispersion being close to zero. A common unit of group velocity dispersion is femtosecond squared per millimeter, and that's because GVD has some unit of time squared per distance. And so since a pulse is on the order of femtoseconds, that we care about this group velocity dispersion, and we see that this pulse gets affected on the order of a few millimeters of glass, so the common unit is femtosecond squared per millimeter. Just a note, this pulse stretching out is strongly dependent on how short the pulse is. So that'll actually be something that you have to show in your assignment as well. But it's why when we talk about these Q-switch lasers, so these Q-switch lasers lasting something like 10 nanoseconds, this pulse can rattle around in the cavity many, many times, and we don't really care about how much this pulse stretches out because it's like a 10 nanosecond pulse. And so a few millimeters of glass is not going to affect that pulse whatsoever. In fact, a few millimeters of glass doesn't really affect pulses even as short as 100 femtoseconds. It's really when we get down to pulses of about 10 femtoseconds, so we have to worry even about a few millimeters of glass. Okay, I'll do a few more slides to talk about what we're going to be talking about on Wednesday. But just to understand what the signs look like, remember the phase is e to the I kz minus omega t. So if you're plotting your pulse in time, normal dispersion will stretch out the pulse like this. So by normal dispersion, I mean you have a prism such that blue has higher index of refraction than red. And that means that you come in and the blue, would be have a higher index of refraction. And so what happens in time is that has a higher index of refraction. So it takes longer for the blue light to pass through the optic than it does for red light. So the pulse ends up being, it's called chirped like this because you have long frequency, or like long wavelengths, and then and then short wavelengths, or low frequencies then high frequencies as you propagate in time. So this, it's chirped just like a bird, and so it goes like boop through the pulse, and so that's called an up chirp. And if I could whistle, that would be what a bird does. But instead, if you take a snapshot of this pulse at time t equals 0, and you wanted to look at this at some, some spatial coordinate, then the pulse is of course flipped backwards because it's kz minus omega t. So this is still an up chirp pulse. So in time, you're increasing in time, you're increasing in frequency, and so this is called up chirp. And this is what happens when you have normal dispersion. When you have normal dispersion in space, that means that it looks like the pulse is propagating to the right, and so the up chirp is going to the end of the pulse, and the end of the pulse is here because this is the back of the pulse. Okay. I guess I'll finish that here, and that's probably all we'll get to on Wednesday's lecture. So that is what we'll be discussing, is a little more detail about dispersion and how the index of refraction of material can affect a pulse.